Imagine for a moment that you've decided to build the most powerful telescope ever created. You've got an unlimited budget, cutting edge technology, and the brightest minds on the planet working for you. Where do you put it? Do you put it on a mountain, high above the clouds, away from the city lights? Or maybe put it on a plane, a flying observatory that can chase totality across the sky? Or, and hear me out here, what if you just launched it into space? Strapped a massive mirror onto a rocket and blasted it through the atmosphere, and parked it in orbit around the Sun, millions of miles from Earth, where nothing interferes with your view of the cosmos. That's not a hypothetical, that's the James Webb Space Telescope. And it's not alone out there. Welcome to What Is, your guide through the strangest corners of human curiosity. And today, we're answering a question that sounds simple, but will take us from the mountains of California to the edge of the observable universe. What is a space observatory, and how does it study the universe? Origins. To understand space observatories, we need to go back to a time when looking up meant looking through something very, very dirty. For most of human history, astronomers did their work from the ground. They'd build towers, domes, elaborate cathedrals of science housing telescopes that could see, well, quite a lot actually, given the circumstances. But they were fighting a losing battle against Earth's atmosphere, that protective blanket of gas that keeps us alive, but it makes astronomy really, really annoying. The atmosphere does a lot of good things. It gives us air to breathe, it protects us from harmful radiation, it makes life possible. But for astronomers, it's the equivalent of trying to watch a movie through a stained glass window that someone keeps jiggling. Everything shimmers, everything blurs. The atmosphere absorbs certain wavelengths of light entirely, blocking entire portions of the electromagnetic spectrum from ever reaching your instruments. In 1946, a scientist named Lyman Spitzer had an idea, and like many great scientific ideas, it sounded completely insane at the time. Spitzer proposed putting a telescope in space, not a small telescope, not a toy, a serious astronomical observatory, orbiting above Earth's atmosphere, with an unobstructed view of the cosmos. He wrote a paper about it, lobbied for it, spent decades advocating the concept, and nobody took him seriously for 20 years. Why? Well, because in 1946 we couldn't even put a human into space. The idea of launching a delicate precision scientific instrument into orbit seemed about as realistic as suggesting we colonize Mars, using only balloons and dreams. But Spitzer kept pushing. He refined his proposals, found allies, and gradually the technology began to catch up with the vision. The launch pad at Cape Canaveral, Florida, October 1968. A Titan 3C rocket roars to life, carrying into orbit a satellite that would change astronomy forever. It's called the OAO-2, the Orbiting Astronomical Observatory 2. It was humanity's first successful space observatory, a proof of concept that proved, against all odds, that Spitzer's crazy idea was actually going to work. OAO-2 carried two ultraviolet telescopes, and it operated for nearly 4 years, observing stars, nebula, and galaxies, with a clarity that ground-based telescopes couldn't match. Ultraviolet light, previously almost entirely blocked by Earth's atmosphere, flooded into its instruments. Scientists have been working in essentially mittens their entire careers. OAO-2 was like giving them surgical gloves for the first time. The age of space observatories had begun. Development. OAO-2 was just the beginning. Once NASA and the international scientific community realized that space-based astronomy wasn't just a fantasy, the race was on to build something bigger, better, and more ambitious. The 1970s brought a string of missions, each pushing the boundaries further. The Copernicus Observatory, the International Ultraviolet Explorer, the Einstein Observatory, which gave us our first X-ray images of the cosmos. Because here's something fascinating. Different wavelengths of light reveal completely different things about the universe. Visible light shows us stars and galaxies. Infrared shows us dust clouds and newly forming stellar systems. X-rays show us violent, energetic events. Black holes consuming matter, neutron stars colliding, the cosmic equivalent of a mosh pit. Ground-based telescopes could only access a tiny slice of this electromagnetic buffet. Space observatories opened up the entire restaurant. Yes, I realize I'm mixing my metaphors here. The point is, the universe is a lot more interesting when you can see all of it, not just the tiny bit that happens to wiggle through our atmosphere. But the crown jewel of this era, the telescope that would define a generation and become arguably one of the most famous scientific instruments in human history, was conceived in 1979 and launched in 1990, the Hubble Space Telescope. Now here's a fun fact that non-astronomy people often don't know. Hubble launched with a flaw, a massive, embarrassing, almost catastrophic flaw. The mirror had been ground to the wrong shape, only by about 1/50th of a human hair. This does sound small, but in telescope terms, it was catastrophic. Images came back blurry. The press had a field day. Newspapers ran headlines calling it the Hubble headache and the billion-dollar blur. But NASA's response is why we remember Hubble as a triumph rather than a disaster. They sent astronauts to fix it. In 1993, the Space Shuttle Endeavour carried up a crew to install corrective optics, like giving the telescope a pair of glasses. And it worked. Beautifully. Spectacularly. Over the next 3 decades, Hubble would produce images that changed how humans see the universe. The Pillars of Creation, the Hubble Deep Field, which revealed that every single point of light in a seemingly empty patch of sky is actually a galaxy containing hundreds of billions of stars. The evidence the universe is accelerating in its expansion, leading to the discovery of dark energy. Hubble was designed for a 15-year mission. It lasted 32. And even now, after its final service mission, it just keeps chugging along, sending back data, expanding our cosmic horizons. But as good as Hubble was, it was limited. It was designed in the 1970s and built with 1980s technology. And as impressive as its images were, there were questions it simply couldn't answer. Questions that would require something much bigger, something more powerful, something that could see further back in time than any telescope in history. That brings us to the present day and the undisputed heavyweight champion of space observatories. But before we get to the good stuff, just a quick note. If you're enjoying this journey into the cosmos, make sure you subscribe to What Is and hit that notification bell. Now back to the largest, most powerful space telescope ever built. The largest and most prominent. December 25th, 2021, Christmas morning. A rocket lifts off from French Guiana, carrying a payload that represents the combined ambitions of NASA, the European Space Agency, and the Canadian Space Agency, the James Webb Space Telescope. Let me give you some numbers to appreciate the scale of this thing. Webb's primary mirror is 6.5 meters in diameter. That's about 21 feet across. That's roughly the length of a tennis court. The mirror is made up of 18 separate hexagonal segments, each coated with a thin layer of gold, because gold reflects infrared light extremely well. If you extracted all the gold used in Webb's mirror, you'd get about as much as you'd find in a small trophy. But that tiny amount, painstakingly applied, makes each segment reflect 98% of the light that hits it. The sun shield alone, this big, multi-layer sheet that keeps the telescope cold and shaded, is the size of a tennis court. It has 5 layers, each as thin as a human hair, and when Webb was launching, the entire thing had to be folded up like origami to fit inside the rocket's nose cone. What makes Webb so revolutionary, unlike Hubble, which operated primarily in visible and ultraviolet light, Webb is designed to see in infrared. This is crucial for several reasons. First, infrared light can penetrate dust clouds that block visible light. When you look at a nebula in visible light, you're often looking at dark, murky patches. In infrared, you can see the stars forming inside, cocooned in the very dust that hides them from our view. Second, and this is a truly amazing part, Webb can see the light of the first galaxies that formed after the Big Bang. This is because the universe is expanding. Light from those ancient objects has been stretched. That's right, stretched, by its journey across billions of years. Visible light becomes infrared. The further back we look, the redder things get, until they finally fade into the infrared spectrum entirely. Ground-based infrared telescopes exist, but they have a problem. Everything emits infrared light, including the telescope itself, the atmosphere, and nearby warm objects. To do infrared astronomy, you need your telescope to be incredibly cold, cold enough that its own heat doesn't swamp the faint signals from distant galaxies. Webb achieves this through that enormous sun shield, which keeps the instruments at about minus 233 degrees Celsius. That's colder than any natural temperature on Earth, colder than Pluto on a warm day. When engineers were testing Webb on Earth, they had to account for the fact that human breath contains enough moisture to frost over the mirror. So they built clean rooms with elaborate air filtration systems. Astronauts wore what looked like full-body diapers, not because of any bathroom situation, but because even the moisture from a single bathroom break could damage the mirror. Webb orbits the Sun, not Earth. It's parked at a point called Lagrange Point 2, about 1.5 million kilometers from Earth. This location was carefully chosen. It's stable, meaning Webb uses minimal fuel to stay in position, and it's far enough away from Earth that our planet's heat and infrared emissions don't interfere with the observations. The trip there took 6 months. Once it arrived, mission controllers spent another 6 months unpacking, unfolding, and calibrating everything. Every solar panel had to be deployed correctly. Every mirror segment had to be alignment checked and adjusted to within a fraction of a wavelength of light. And then it opened its eyes. What are they looking for? So Webb is operational. It's in position, its mirrors are aligned, its instruments are cooled, and it's taking images that make astronomers weep with joy. But what is it actually looking for? What's on the scientific shopping list for the most expensive telescope ever built? The science goals fall into several major categories, and each one represents one of the biggest questions in modern astronomy. First up, the early universe. Webb is designed to observe objects that formed in the first few 100 million years after the Big Bang. This is an epoch we've never directly seen. We've had theories about how the first stars and galaxies formed, but we've never had a telescope capable of testing those theories. The light from these objects has been traveling for 13 billion years, stretched into the infrared, incredibly faint and easily confused with other nearby objects. Webb's infrared vision and massive mirror make it uniquely capable of piercing this cosmic fog. Already, within months of first light, it has found galaxies that shouldn't exist by our previous models. Massive, mature galaxies that seem to have formed too quickly after the Big Bang. This is the kind of problem astronomers love. Not a crisis, but an invitation to revise our understanding. Second target, exoplanets. That's the term for planets orbiting stars other than our Sun. Since the first confirmed detection in 1995, we've discovered over 5,000 exoplanets. Most are giant gas planets like Jupiter and Saturn, because big planets are easier to detect. But as our techniques have improved, we've started finding smaller, rockier planets in the habitable zones of their stars. Not too hot, not too cold, where liquid water could exist on its surface. Webb isn't designed to take pictures of these planets directly, not usually anyway. Instead, it analyzes their atmospheres. When a planet passes in front of a star, some of the starlight filters through the planet's atmosphere. Different molecules absorb different wavelengths of light, leaving a chemical fingerprint. Webb's instruments can read those fingerprints, detecting water vapor, carbon dioxide, methane, and potentially even signs of biological activity. Is there life out there? Webb won't answer that question definitively, but it will tell us which worlds are worth investigating further, which atmospheres look like they might be doing something interesting. Third major category, stellar life cycles. We understand the basics. Stars form from collapsing clouds of gas and dust. They spend most of their lives fusing hydrogen into helium. They die in different ways depending on their mass, peacefully for small stars, cataclysmically for large ones. But the details are murky. How exactly do stars push the leftover material back into space to seed a new generation of stars? What happens inside a nebula where dozens of stars are forming simultaneously? Webb's infrared vision cuts through the dust to reveal these stellar nurseries in unprecedented detail. And then there's the weird stuff. Webb has observed the collision of two neutron stars, an event that creates half the heavy elements in the universe. It's watched a black hole devour a star, an event called a tidal disruption. It's looked at Jupiter and found unexpected features in its atmosphere. It's examined the atmospheres of planets in our own solar system with instruments that would have seemed like science fiction just a generation ago. But for all its capabilities, Webb isn't the end of the story. It's not even the only game in town. The future. The history of space observatories is a story of constantly pushing outward. Each generation builds on what came before, answering some questions while revealing entirely new mysteries. So what's next? Several major missions are already in development. The Nancy Grace Roman Space Telescope, named for the pioneering astronomer, is currently, at time of recording, scheduled for launch in late 2026. It's designed for wide-field infrared surveys, capable of mapping large swaths of the sky with Hubble-quality resolution. Roman will hunt for exoplanets, study dark energy, and potentially discover entirely new phenomena, simply by observing at scales we haven't yet explored. On the ground, the extremely large telescope is being built in Chile, with a mirror 39 meters across. That's larger than a basketball court. Ground-based telescopes will never match the clarity of space observatories, but they can be built much larger and updated more easily. The next generation of ground-based giants will work in concert with space telescopes, providing complementary capabilities. China is constructing the Jiutian Space Telescope, which will have a field of view 350 times larger than Hubble, allowing it to map huge portions of the sky. India has expressed ambitions for its own space observatory missions. Private companies are discussing space-based telescopes that could be built more cheaply and launched more rapidly than traditional government missions. But perhaps the most exciting developments aren't about any single telescope. They're about the convergence of capabilities that will allow us to finally answer questions we've been asking for centuries. Direct imaging of exoplanets, not infrared from wobbling stars or dimming lights, but actual pictures of worlds around other stars. Several missions in development aim to do this, blocking out the glare of the parent star to reveal the faint reflected light of planets. Gravitational wave detection from space. Ground-based detectors like LIGO have revolutionized our understanding of black holes, but they are limited to the most violent collisions. A space-based gravitational wave observatory could hear the gentle whispers of supermassive black holes merging, potentially taking us back to the first moments after the Big Bang. Studying the nature of dark matter and dark energy, these phenomena make up 95% of the universe, and we still don't understand what they are. Future space observatories will map the distribution of dark matter through gravitational lensing, and measure the expansion of the universe with unprecedented precision. And always looking deeper into the early universe. Webb can see the first galaxies. What comes after will see the first stars, and perhaps, eventually, the cosmic dark ages before any light existed at all. This is the great adventure of our species. Every space observatory, from OA02 to Webb and beyond, represents humanity's collective effort to understand our place in the cosmos. So what is a space observatory? More than a telescope in orbit, more than a scientific instrument. It's an extension of human curiosity, a way of seeing that transcends the limitations of our home planet. We built OA02 because Lyman Splitzer refused to accept that the atmosphere had to be a permanent wall between us and the universe. We built Hubble because we wanted to see clearly. We built Webb because we wanted to see further, deeper, and in wavelengths we couldn't previously access. And we'll keep building them because the universe keeps revealing new layers of complexity, beauty, and mystery. If you found this journey through the cosmos fascinating, hit that like button. For more content that breaks down the biggest questions in science, space, and human knowledge, subscribe if you haven't already. Because here's the thing about exploration. It never ends. Every answer generates new questions. Every horizon once crossed reveals another beyond. The universe doesn't care if we're confused. It just keeps expanding, evolving, and existing on scales that make our existence seem brief and improbable. And yet here we are, a species of hairless primates barely 300,000 years old, building telescopes that can see back to the very beginning of everything. That's remarkable. That's worth celebrating. And that's absolutely worth subscribing for. Until next time, keep looking up and keep asking what is. See you next time.